Hello everybody, and welcome to our webinar this morning, an introduction to variable frequency drives, hosted by myself and William Cameron, the product manager for automation and drives at Electromechanical. And sensors, let me not forget that, William.
And power supplies.
And power supplies. It's really encouraging to see how many people have joined this morning. Thank you everybody for your time. In these challenging global times that we currently face. Yeah, let's get stuck into it. The goal of this morning is to give you a broader understanding of variable frequency drives. How do they operate? What are the logic systems behind it? And hopefully give you a better understanding as to how to choose the correct product going forward. As I said, my name's Conrad. William is the presenter. Just before we get going, there are some functionality options you have available to yourself. You have a chat option on the bottom toolbar of Zoom, where you can ask anything. If you're having any technical issues, you can pop it in on the chat option. If you want to ask a live question, you can raise your hand. And if you have a question that you want to type through to us and let us answer during the webinar, you have the Q&A function as well. Please, we're looking for an interactive session. We really want to engage with you and to get you asking questions so that we can help and assist wherever we can. At the end of the session, we will have a poll. Takes 1 to 2 minutes to complete. Just helps us for our next webinar to make sure that we offer you the most engaging and interactive session that we can. So there you can see a layout of the contents. We'll be looking at the basics, pros and cons of drives versus DOLs, single phase and three-phase drives, applications, pumps and fans, the energy saving aspects, and pump laws. Then we'll have a quick 5-minute interval, enough time to make another cup of coffee. And then we'll dive into some more technical aspects, closed loop control, water pressure, level control, air pressure, comparing the old EL versus the new ME 300, and then basically wrapping up from there. Thank you very much. William, over to you.
Thank you, Conrad, for the introduction. Hello all. Another quick one before we get started. It would be best if everyone could have their 2020 catalogs on hand. During the presentation, I do reference to particular pages just to add a little bit more value to the slide. So please, if you can, keep your 2020 catalogs on hand. You'll see from time to time a page number will appear in the top right corner. And like I said, it'll just add more reference to the slide if we could look at the page as well as the slide itself. All right. We're looking at about 75 minutes, so it's an hour and a quarter, plus minus. That's the duration. All right, let's go. I always like to start at the beginning, just so we make sure we're all on the same page. So a little bit of motor basics before we get into drives. You can see by the animation, it's one of my favorites, how the field and vectors pull the rotor around the stator of the actual motor. So as your phases rotate, that induces the force on the rotor to follow that phase rotation. It's a very simple formula to work out the speed of a motor. It's basically 120 times the frequency of the rotating phases divided by the pole pairs of the motor. So obviously looking at the basic formula there, you can see by changing the frequency, we can control the speed of that motor. So by changing the F component, the frequency, which is exactly what the variable frequency drive does, we're able to control the speed of that rotation. A quick look at contactors versus VFDs. People often ask why a drive and why a contactor. So let's just break that down quickly. Here's a basic direct online starting circuit. You've got your power circuit on the right-hand side over here, and then you've got your control circuit on the left-hand side. This is as basic as it can get for a direct online circuit. You can note the D-curve breaker above the contactor itself, and the overload all need to be connected in the power circuit. So when switching on a motor on direct online, there's obviously a lot of forces at play. As you can see by the video, we'll play it one more time. Start over here. The torque generated at startup is quite immense, enough to make the motor even wobble a bit at startup. And obviously that mechanical stress is transferred along the shaft to the belt drives, to the conveyor, to the pump, to everything else. And we can see it's quite a rough start. Just looking at the switching current of that motor as it starts up. As the motor goes from 0 speed to its full speed, typically 1,500 RPM, it induces a large current draw, sometimes up to 10 times the motor's rated current. This is why contactors have the AC3 rating, to handle that high startup current drawn by the motor. Because at rest speed to maximum speed, it does that in less than 1 second. Looking at a drive's power circuit, it's a little bit more complicated, as there's 3 main sections. Your first section, where the drive converts the AC into DC, the rectifier section. The second section, where that rectified voltage is then filtered to a more stable DC bus value. And after that, the inverter piece, where the drive switches in a particular pattern to create the simulated AC sine wave. Just looking at that simulated AC sine wave a little bit closer, the drive simulates the AC. So it's not a pure AC wave, but enough for the motor to think it is. So you can see the drive can control 10 hertz, 20 hertz, 30 hertz, or any speed in between those values. And by doing so, changing the switching pattern of the drive's inverter section or of the IGBTs. Just looking at the drive's control and power circuit, it's a lot simpler than that of a direct online starter. All the protection is built inside of the drive, and the breaker is just here for cable protection. The controls are made a lot simpler because again, all the logic is built inside of the drive, so your controls can be simplified. Just looking up at a startup video of a drive versus the previous video.
The default speed reference is 60 hertz.
You can see from startup to stop, very smooth transition, no jerk in the motor. This is because the drive can control the hertz from 0 to 50 hertz. And by not having an instant change from 0 to 50 hertz, but having a gradual change that the user can set, by doing that, you can control the amps as well that are drawn by that motor. So the drive controls the slope of the frequency change, therefore it can control the amps drawn by that motor. The startup can be anything from instant, 0.1 seconds, not really advised, all the way through to 600 seconds and more. So you have a great amount of versatility using the drive as your startup procedure. You can also note that the breaker used, we don't need a D-curve, which is a little bit more expensive. With the drive, because you don't ever hit those peak currents, a C-curve breaker is good enough. Just a quick overview of the pros and the cons. I'm not going to go through all of them. Contactor pros, there's only a few to mention. It's a lower initial cost. There's less heat generated by a contactor compared to a drive, and generally a smaller footprint in your panel. Not much else is in favor of contactors. Where in drives, you've got full control, phase failure, phase reversal, energy saving, less mechanical wear, flexibility for the application, and the list goes on and on and on. Having a look at our VFD range, we have quite a substantial range to offer, and it's quite important that as a client or a potential client that you understand the differences between each range. Some are more economically priced, some have the particular features that you might need for the application. So it is rather important that we are familiar with the differences over the ranges. Quickly, the ME is our entry-level drive, ultra compact and economically priced, single phase to 2.2 kilowatt and three phase to 7.5 kilowatt. The MS is its bigger brother, a little bit more intelligence built in, same range for 220 volt, and up to 400 volt, we go to 22 kilowatt. The C2000, we're actually going up to 560 kilowatt. Apologies for that, the slide is slightly out of date. That's for your heavy duty crushers, cranes, etc. CP2000, fan and pump purpose drive. ED is our elevator purpose drive, and our E is, I would call it the general purpose drive. It's got a little bit of everything inside. Another important one to note is the part number breakdown. Some VFDs have a slightly different naming rule to others, and I'd just like to highlight that quickly. So if you take your attention to page A20 in the catalog, where the VFD E drives reside, we'll just have a look at that part number breakdown quickly. So in the E drive, the VFD is obviously the prefix that's used for variable frequency drive. Then it's followed by the kilowatt of the drive. 007, excuse me, would mean 0.75 kilowatt. 022 would mean 2.2 kilowatt, and 220 would mean 22 kilowatt. Followed by the drive series, and then 21 for 220 volt single phase, or 43 for 400 volt three phase. We won't see drives ending in 11 and 23 because we don't have these types of voltages typically in our country. Unless it's a special machine with a unique transformer to supply the drive, we won't be using any drives with these codes. So E drives followed by a 2-1 or followed by a 4-3 is typically what we would use. Just having a look at the previous page, page A19, where the MS and ME300 are. Delta have changed the naming rules slightly for these M series drives. You can look over here, they still use the same prefix of VFD. But the next version is where the main change comes in. It's no longer the actual kilowatt of the drive, but rather the rated current of the variable speed drive in its default duty mode. So this MS drive in question is a 4.8 amp drive. I'll repeat that, that is 4.8 amp drive. So a VFD that says 2A8 is 2.8 amps, or 2A7 is 2.7 amps, and so on. So that's the main difference between the naming rule of the MS, ME versus the rest of the ranges. Followed by that, we'll have the code MS or ME, again 2.1 or 4.3 for the rated voltage, the rated input voltage of the drive, and then a number of version options for that particular series. A21 and A22, we're looking at the C2000 and the CP2000 series. Here we go back to the conventional naming rule of kilowatts in the part number and not the actual rated current of the drive. You'll note that the C series, we don't have 220 volt single phase options, but 400 volt three phase, 575 volt three-phase, and 690 volt three-phase options available.
William, we've got 2 questions that have come in.
Cool.
The first one from Niha. Are the motors connected in star or delta of a VFD?
Well, that depends on the motor. Typically on a, let's go back a few slides if you don't mind. If your drive is typically a 220 volt single phase drive, then your smaller motors will be connected in delta, 220 volt three phase delta. So it's important that if your drive has a 220 volt rating, that means the output voltage is also 220 volt. So look on the nameplate of the motor. It will have 2 connections, star and delta, most likely. You need to connect it in delta, which is a 220 volt three phase connection. Typically for star motors, for 400 volt motors, the typical connection would be star. Again, this is a general rule. It's not a blanket rule. You really need to look at the motor's nameplate to decide how that connection would go. Hope that answers your question.
And then the second question is from Mike. Do all the drives have a communication protocol such as Modbus?
That is a very good question, and I don't think I've mentioned that in the slide. All the Delta drives have built-in Modbus. Every single drive, from the most economical all the way through to the high-end drives, have built-in Modbus. In fact, the pump purpose drives, the CFP and the CP2000, also have built-in backnet communication for BMS systems. But to go back to the original question, every single variable speed drive Delta have to offer has a built-in Modbus RS485. You'll notice some of the versions, the higher end versions, will have additional field bus cards, so Ethernet, IP, EtherCAT, Profibus, etc., etc. But as a standard, all with built-in Modbus RS485. Works very well with our PLC range, and is something we promote quite often.
Great. And then one's just popped in from JJ Kruger.
Hello, JJ.
Are there any developments in the future regarding the PLC, so the drives as a master and slave for onboard PLC?
There will be a video a little bit later on describing something like that, where the CP2000s can be configured in a master-slave scenario. That is very new, and I want to say I haven't wrapped my head around it too much, but it is possible to have a drive in a master-slave situation. I know that the C2000 variable speed drives can be a CAN open master to a network. And if I remember correctly, my colleagues would confirm with me, we've even done C2000 using a mod read instruction, reading another PLC or an IO block to extend the IO of that actual C2000. So yes, C2000, as far as I know, 100% is the only drive that can be used as a master. But it doesn't have the functionality of the PLC link like you enjoy inside of the PLC software. It's more of a manual mod read, mod write instruction targeting particular registers. So JJ, to answer your question, ultimately, there's no development that I know of including PLC link as the driver, let's call it, inside of the VFD PLC software. But the C2000 can do mod read, mod write. Okay, let's go back to where we left off. CP2000, much the same as the C2000, just with the added suffix here of -21, which indicates it has a IP21 rating. Okay, so most of the drives have kilowatts in the part number breakdown, except for the MS and the ME300. They have the drive's rated current in the part number breakdown. Another question that comes up quite often is three-phase and single-phase. I have a single phase motor. Do you have a variable speed drive? No, we don't have a variable speed drive for a single phase motor. We have a variable speed drive for a single phase supply, but that output of that drive is still 3-phase 220 volt. Like previously discussed, most likely a delta connection on this motor and most likely a star connection on the 400 volt 3-phase motor. So again, 400 volt 3-phase in, 400 volt 3-phase out. Single phase 240 in, 3-phase 240 out. We're going to have a closer look at our pump and fan particular drives, namely the CP and the CFP. Pumps and fans are quite a big industry for everyone, I'm sure. So I think it's worth having a closer look at these drives. So like I mentioned before in the range breakdown, we have a large amount of drives to choose from. Some of them are good in their own aspect in their particular applications. But when it comes to the pump realm, I'd just like to highlight what drives I would suggest and for what ranges that those drive series are available in. So the ME300, our entry-level drive, very good for pumps for a low-cost system. The only negative here is we stop at 7.5 kilowatt. Okay, so if you need an 11 kilowatt drive, the ME300 won't be your pump drive. The MS300, much the same, very good for pump applications, a lot of built-in pump features, and that goes up to 22 kilowatt max, so nothing more than that. The E-drive is generally low on pump protection parameters and features, so I wouldn't suggest it for a pump application. But if you just need to turn a pump, the E-drive will do the job. CP2000, on the other hand, is probably the best drive for all pump applications, except for when your supply voltage is only single phase 220. We don't have an option in the C2000. We've got another question here, Conrad.
Yep.
220 volt input, single phase with 3-phase 380 volt output? No, no. You would need to do some fancier external boosting voltage circuit to get that right. But from Delta and from EM, we don't have a catalog solution for that, no. No. Sorry, John. Back to the CP2000s. So great for anything using 400 volt drives, all the way up to 560 kilowatt. So from 1.5 kilowatt, we can supply up to 560 kilowatt as a pump purpose drive. The CFP, like the name suggests, is very close to the CP, except this drive has an IP55 protection rating and only goes up to 90 kilowatts as a maximum. So also very good for pumping industry, especially if you want to wall mount the drive and you don't want to use an enclosure. CFP is absolutely perfect. The C2000 is just too expensive. There's no reason to go for the C2000 on a pump purpose drive, on a pump purpose application. It's priced out. It's got too many features that are not pump related embedded in the drive. So you're paying for something you're not going to use, basically. And last but not least, our ED drive is very particular to elevator applications. So extremely low on pump parameters and also costly compared to the CP version drive. So I hope this table explains our offering with regards to pump specific drives a little bit more. And when a customer asks you to quote him, that it'll help you choose the correct drive for the application.
Another question?
Yeah. Would it be possible to combine the use of drives with generators, whether in residential area or industrial area, depending on the size of the generator and application? Yes, a lot of our clients have used drives to supply generators to supply the drive. Apologies. A lot of our clients in Zimbabwe, especially in the agricultural area, they don't have another means in actual fact. So I would say 60–70% of the pump houses are probably run by generators. There are some tricks. Some generators might not like the non-linear load of the drive. I would just confirm that with the generator supplier. There's a lot of literature on the internet about running generators from drives, but definitely is possible and something we do quite often. Some more questions coming in. What will be the connection protocol on these drives with HMI? Well, there's a number of options. If you don't want to add any extra facilities, the HMI talking directly to the variable speed drive over the built-in RS485, in my opinion, is absolutely perfect. The Delta HMI has a host of built-in drivers. You can just go select I normally use the Delta ASCII controller, and from there you can select Delta inverter and target the address you want to display on the HMI. Change the ID if you've got more than one drive. It really works well directly from the HMI to the drive's built-in Modbus RS485. You could also add Ethernet cards onto the drive and talk Ethernet back to HMI that supports that. That's another option. But right out of the box, the RS485 to the drive really works fantastic. We do it quite often. Another question from Chris. Hello, Chris. Hope you're well. Does Delta have any regenerative front-end drives or any resistor bank functions? Yes, we do. If you look in the catalog, you'll note most of our drives up to 30 kilowatt have built-in braking choppers. So you wouldn't need an additional braking unit, just connect the resistors directly to the drive. So typically about 37 kilowatt and up, you would need an external braking unit, and then resistors are connected on that separately. Front-end drives, yes, is called the Delta AFE2000. That's Delta's front-end application. Regenerative drives as well, yes, that is called the REG2000. We haven't sold any AFE2000s in South Africa, but we have sold quite a few pieces of the REG2000. A purely regen unit. So instead of your brake resistors, you would have the regen unit on the output. And when braking is done and regen happens, that regenerative unit takes that energy and switches it back into the mains so that you don't dump it and waste the energy in a form of heat, but rather reuse that energy back into the grid. Common in lift application and hoists. I think if the building wants like a green stamp, they might need to do that. We've got one in our lift in Cape Town. And we also use a couple of them on our load test benches. So when we load up motors and test our drives, we use the regen unit to recirculate the regen power. So Chris, AFE2000 and REG2000 are the specialized regen and active front ends. And all the Delta drives up to lower than 30 kilowatt have built-in braking choppers, even from the most basic ME all the way through to the high-end CP2000, all have built-in braking transistors. All right. Like I mentioned, we're going to focus on the pump particular drive. So page 822, 823, we can see the CP2000 and CFP2000. Just highlighting them again. C2000, IP2021, depending on if you add on the extra conduit box or not, and depending on the frame. CFP2000 is IP55. This is a new one to our catalog, the CFP2000, and it's been doing great thus far. So in every fact, it's identical to the CP2000. If you're doing the programming inside the PLC or reading parameters out, the controls, the parameter grouping, the addressing, it's identical to CP2000. except it has extra filters to reach a better noise level, a better EMC level, and it's obviously got the IP55 housing, which makes it really, really well suited for HVAC applications. You'll note on the CFP, there's two models that Delta manufacture, one without a front isolator and one with a front isolator. We've made the decision to stock without front isolator based on feedback from certain clients. But if you require with isolator, we have a few pieces in stock, not as much as we stock without isolator, but we can still procure it for you. So please, Delta have both options, with and without isolator, which are both available. So CFP2000, a quick deeper look at that. Very, very high enhanced PCB coating. It's the highest compared to all the other drives. As I mentioned, very low noise capabilities of this drive, so it can reach quite a high EMC class, and obviously as well as its IP55 protection rating. All right, let's have a look at the energy saving principles of fans and pumps. These applications are typically where you would save, in my opinion, the most energy is in your fan and pump application for the reasons that will follow. The affinity laws is a set of law that describes centrifugal systems, rotating pumps and rotating fans, basically. The law basically describes the relationship of RPM versus flow, pressure, and power. So the first part of the law describes flow is directly proportional to speed. Just kind of makes sense. The faster your pump turns, the more flow you get out. And this is a proportional relationship. I see there's another question. I'll just park it here. On your smaller Delta drives in the range of 2.2 kilowatts, how can I get drive settings off if front pad screen is damaged? Good question. Like mentioned before, all the drives have built-in Modbus, RS485. So depending on the drive model, there's normally like an RJ45 socket on the drive. That is the socket that has the Modbus terminals in it. So using our part number IFD6500, it's a USB to RS485 converter. The USB plugs into your computer, and obviously the output, the RS485, will connect to the drive. And then using VFD soft, you can extract the parameters from that drive and save it in an Excel format or a CSV format. Save those parameters. You can compare in the software, you can even compare the default parameters versus the parameters in the drive. So instead of having a very long list of settings, you could just tell it to highlight the settings that have been changed from the default. And it normally is just a handful of parameters that you need to look at and not a long list. So VFD soft, that's the software you need for your computer. And the IFD6500 USB to RS485 connector. In that box, you'll have all the cables you need to connect up to the drive, to link your PC to the drive. And that should work. Okay, back to the pump laws. So we know flow is proportional to RPM. That is, it makes sense in our heads. The next part of the law will describe pressure or head. And here, pressure is proportional to the square of the RPM. And the last part of the law, the one that really matters to me, is comparing RPM to the power component that the pump would draw. And importantly, RPM is power is proportional to the cube of the RPM. So you can see the table that is drawn up via those three laws. If we highlight only on the power section, you would note that dropping a small portion of RPM, because of the hyperbolic curve of the cube, would save a large amount of energy. So even the finest reduction in speed from 50 Hertz to 45 Hertz over a long period of time can save quite a substantial amount of power. Another graph to describe this is your typical throttling valve. If you throttled it almost all the way back to zero, the power drawn by your pump is still around 60 to 70%. And obviously, as you open the throttling valve, the flow increases and the pump does a little bit more work. So that's generally the difference in load that a typical throttling valve would put against the pump. So when you're adjusting your throttling valve to set your pressure right, you're still using a lot of power. The valve is just taking the knock and getting rid of the energy via noise and heat and whatever else. But if you look at the drive's theoretical curve versus the pump, you'll note that they follow each other very, very closely. So the slower you run the drive, the less power you draw. This is accordance to the affinity law. So this is the area that I've highlighted is where you save power. In my opinion, this is where you save the most power. If you're going to be running your drive at 50 Hertz all day, every day, then you probably won't save as much power as you would have hoped for. You would save a little bit in maintenance and power factor, etc., but not the bulk of the energy saving potential that you would enjoy if this pump was running at variable speeds compared to a throttling valve. And just the last graphic explaining that situation. Without the valve and a VSD, the power that you require to do the job to water the plants and the input power that you draw to do that job are very close to each other. However, in the typical mechanical valve situation, your input power versus the power that you actually require to do the job are disproportionate. And generally, you are wasting energy in this case. All right. Hi, Daniel. Yes, we will share the PowerPoint. If you've registered for the training, you will get a copy of the video. If you want a copy of the actual PowerPoint presentation, then just send me an email. Conrad, if you can just take Daniel's details down, and I'm sure we can send the actual presentation if that's what he wanted. But automatically the video will be sent to you after the presentation. All right, geez, that time already. Time to get a cup of coffee and go to the loo if you need. I'll leave you in the hands of a colleague from Delta to give a little bit of entertainment in the break. If you want to watch it, be my guest. I'll see you guys in 5 minutes. Oopsie.
This is Delta.
Oh, your father. Okay, get your wife. You know what? Take it good.
Hi, I'm Nader Suleiman. The variable frequency water supply system is a mechatronic system which can be used with pump sets. It integrates 80 variable frequency speed regulation and microcomputers control technology into automatic pump controller. Based on the pressure and the flow rate of the pipeline, the system automatically regulates the number and the speed of pumps in operation for closed-loop control of constant pressure and variable frequency water supply, improving quality and saving energy. The variable frequency water supply system is widely applied in fire water, domestic water, industrial water, as well as sewage treatment system. Now we'll be talking about the features and advantages of the system. The system has three main features. First, it provides floating master control for higher reliability. Each device can be set as a master. In case of a master failure, the device with the highest priority automatically switches to a master mode to take over system control. Also, the master controller is automatically back to place and regains system control after the fault is cleared. Secondly, this solution is considered a state-of-the-art control solution for longer service life, as it provides a real-time recording of the motor operating time and makes sure to start the motor with the shortest operating time and stop the motor with the longest operating time. Also, it provides the timing cycle control to avoid long-term stop of motors. And last but not least, this is an efficient solution, which gives the system an edge. It provides quantitative and uniform frequency control for efficient operation of pumps. For more information about Delta Industrial Automation product, please visit www.deltaww.com. Thank you for watching.
JJ, I don't know if you're still there, but regarding your question on the PLC master-slave scenario, to be honest with you, I don't know how Delta have done it inside of that CP2000, but they have managed to have floating master with multiple slaves. They do that with the internal PLC of the CP2000. That software is free for anyone to use who wants that solution. But where all the intelligence is done, those function blocks inside of the PLC program that Delta developed are locked. So we can't can say reverse engineer 100%, but I'm sure if I ask Delta for the information on how they got it right, we will be able to get it. That shouldn't be an issue. Hi, Nahar. Which PDF manual of what drive are you referring to? I can send it, no problem. CP2000? CP2000. Okay, not a problem. Is your email address on the attendee list? Let me make a note quickly of that. Or Conrad, you're not doing anything. Can you please make a note to send Nihar a CP2000?
You already had a little bit ahead of you, hey?
Thank you. At least you are doing something. All right, guys, I hope you're still with me. Let's continue with the last half of the webinar. So in this part of the webinar, we're going to be looking at drives in conjunction with field devices, namely analog transmitters for level and pressure. And using these field devices, we can set up control loops and allow the drive to interact with this environment on a much more intuitive way than otherwise without the field devices. So we're going to have a look at a couple of the more common types of closed loop controls using the Delta VSDs as well as some of our other suppliers' field devices. One of my favorites must be constant pressure control. So using our Huber 5-8 or 5-0 type transducers in conjunction with the variable speed drives, we can form a closed loop pressure control. So we've got a number of transducers that we offer and stock. General purpose 0 to -1 or 0 to 60 bar for your general type applications. Ultra low pressure measurement even lower than 0.6 bar, I believe. 520 for more high burst demands, and certain aggressive refrigerants as well. That's immune to those. Also our 540 and 548, very similar to the above, except they got the digital display and extra digital outputs with particular control functions with the general analog retransmission as well. Typically 4 to 20 milliamp would represent 0 to the pressure range of the transducer that you selected. So 4 milliamp would be 0 bar and 20 milliamp would be, let's say, 10 bar. And that information, that 4 to 20 milliamp signal, is what the drive would read as the actual pressure in the line. That's on page K23, our Huber transmitters. So having a look at the closed loop control that the drive does, there's a little bit of mathematics built into the drive. Well, not a little bit, a lot. And it uses the output of the process to feed back into itself and to either increase the speed of the pump or decrease the speed of the pump based on what the user wants in terms of the set point, how many bar do you want, and obviously based on the output it senses back from the field. So to replace that with some graphics, we've got the process, which is the pump, the drive, which is the brains, the set point comes into our control terminals, and obviously the Huber transducer would send back the pressure signal to the drive. This forms our closed loop control. So any action has a reaction that takes place. Having a look at a few applications for closed loop control, there's one where you have a constant pressure set point. I want to maintain 5 bar at all times in this pipeline. And by setting a constant pressure set point, if you have an increasing demand for water, you would automatically have the drive speed up. So if I have a constant pressure for 100 apple trees, I only need 1 cube of water. For 500 apple trees, I need 5 cubes of water. And 1,000 apple trees, I would need 10 cubes of water, for instance. By keeping a constant pressure in the line, automatically the speed of the pump would have to change to compensate or to give the amount of water, and to keep the pressure constant, it would have to increase the flow. So increasing demand for water with a constant set point, easily achieved with this combination. Another application would be to compensate for elevation. If you're farming on the side of a mountain or in the hills, for instance, this is probably something that you would do quite often. If you are watering the same amount of apple trees, set point 1, set point 2, and set point 3, or zone 1, 2, and 3 on your farm. Zone 1 is at sea level, so set point 1, where zone 2 is 30 meters above sea level. So it would be set point plus 3 bar, which equates to 30 meters. And obviously for the apple vineyard or orchard, sorry, that's 50 meters above sea level, you would need to go the original set point plus 5 bar. So by sending these new set points via digital signals to the drive, you can easily compensate for elevation in your farm. Obviously as well, the drive would need to speed up to get over that elevation issue as well. All right. Yeah, 10 meters of water level would be 1 bar of pressure. That's just a general rule that we can apply. So 3 bar, 30 meters, 5 bar, 50 meters. 10 meters of water level equals 1 bar of pressure. Okay, looking at the level sensing transducers, so moving away from constant pressure and looking at constant level as a closed loop function, we obviously need to use different types of transmitters. So for that, we'll use the type 712 and 713. If you go to page K24, you'll see them there on the bottom right. So type 713, typically for borehole and dam measurement systems. Why borehole? Because the unit comes with an attached cable ranging from 75 meters, I think we do from 80 meters, 100, 125, all the way through to 175 meters of cable actually attached to the transducer, sealed inside the transducer. So if your borehole is 100 meters deep, you would choose a transducer with, say, 125 meters of cable, just to give you a little bit of extra on the top of outside the hole. And knowing that 1 bar equals 10 meters, the 10 bar range 713 would be enough to measure the full scale of 100 meters and still have an additional 25 meters of electrical cable outside the hole. Looking at application where you want to keep a constant level in a JoJo tank and perhaps not a borehole, then you would look at the 712s. They have a shorter cable length and obviously a lower pressure range. So, you know, good for your typical JoJo 3 meter high or 10 meter high. I guess that's quite a big JoJo tank still, but your general holding tanks, 712 would work well here. So that's the 712 and the 713 for constant level. That's how the transducer would look. You can also see it on page K24. So this being a level transducer, it still actually works on a pressure system. So it would measure the pressure of the water that's exerted above it. Sometimes also referred to as a hydrostatic sensor, using the word hydro in water and static as in static pressure applied on top of the transmitter. Interesting point, inside the cable that runs the length of these transmitters, there's actually a small air pipe. This air pipe continuously would measure the air pressure above ground as a reference point to the pressure in the well or in the tank. The pipe is there so to be exposed to atmospheric, like I said, to measure this difference, so that the sensor is scaled for life, basically. There's no absolute setting and there's no drift. If the pressure changes, when anything changes, the sensor can detect and compensate as well. So that's this tiny little 1 or 2 millimeter pipe that's exposed to atmosphere. If you blow or suck on that pipe, you would physically see the level or the signal actually change as you're changing the reference point of that transmitter. So again, PID, this time with level control. By simply setting the PID to what they call negative feedback or a positive feedback control loop, we can easily change the drive's application to an emptying application or a filling application. So are we emptying out the tank or are we filling up the tank? So that's easily achievable just by changing one parameter in the drive to emptying or filling. Positive feedback, as it's called, is normally related to emptying of a vessel, and negative feedback would be to fill up the vessel. So having a look at those filling and emptying scenarios in a closed loop. In scenario 1, if my set point was represented by this dotted line, if the function was emptying in scenario 1, my pump wouldn't do anything at this point. At this level, it wouldn't do anything because I'm well below where I want to be in my set point. And if I turn the pump on now and I'm set to emptying, I'm going to take out more water. I'm not going to fill it up. If the function was set to filling, and this was the scenario, the drive would obviously turn on and fill up until the pressure transmitter would measure that type of level. And vice versa, if the scenario was reversed, then the emptying function would take effect over here, and the filling function would obviously be, wouldn't run the pump. So it's important to notice in the closed loop realm that the bigger the difference between the set point and the actual feedback value, the faster the drive will work. So if the difference is very large, i.e. an empty tank and I need to fill it, the drive would go at full speed to try and fill the tank. It'll notice how fast the tank is filling up and slow the drive down as to not to overshoot the actual set point. If set up correctly, the drive and the system should maintain perfect level at all times. i.e. if the pump has enough capabilities to fill up the tank or empty the tank in time, it will maintain perfect level, no doubt. Just having a look at a couple other options when it comes to emptying and filling. Page K9, we have the ultrasonic setup. So also works with the analog signal and a closed loop back to the variable speed drive, except here you've got a non-contact solution. So you use an ultrasonic to detect the time of flight from the water surface back to the sensor, and that would be then the height of the water in the tank. Great for applications in sewage or in contaminated liquids. You wouldn't want to put your nice 712 into a sewage sump, for instance. You would rather use ultrasonic. This way you can keep the level constant and not make contact with the fluid. And obviously the most basic type, a purely digital solution. So the on and the off point will be completely decided by the differential of the actual float switch. Very little control, but obviously a very cost-effective solution. This type of digital system you could probably even use with a direct online, and probably most common with a direct online as well. Back to pressure control, but this time air pressure control. We'll highlight our 699 Huber transmitter. 4 to 20 or 0 to 10 volt out, and this unit will detect the air pressure difference between 2 points, namely P1 and P2. This is why it's called a differential pressure transmitter, because the pressure at P1 and the pressure at P2, the analog signal that's transmitted is the difference between these 2 points. That's on page K25. So a quick application for the 699 would be to keep a constant air pressure in a stairwell. So here's your stairwell. Here's your ducts, your air ducts. In a case of a fire, or in general, you always want a positive pressure in your stairwell. So if there is smoke inside the building over here, the positive pressure kept in the stairwell would keep the smoke out of the stairwell, allowing valuable time for people to make the escape down the staircase. So P1, for instance, will be connected inside the passageway. You'll have your little pipe running into the general corridors of the building, and P2 would be situated inside of the actual stairwell. You would then tell the drive, I want to keep a difference of 20 millibar or whatever the value is, and the drive will always try and maintain the difference in pressure. If people start to open up these doors and the pressure maybe starts to equalize because multiple doors are being opened and people are trying to escape the fire, obviously the drive will then ramp up and try maintain that positive pressure even further. Even though doors are being opened or closed, the drive will just react to the pressure difference and do its job. So important to keep the stairwell smoke free and allow people time to escape in case of a fire. That's a typical example for our 699.
Got a question from Trevor regarding ultrasonic sensors.
Ah, the foam question. Yes, I love it. It probably will pick up foam. I have seen different solutions for foamy water. Often they would have a pipe running down into the actual fluid, so that the foam will be building up around the pipe. Cut the pipe at like a 45 or 60-degree angle and put that into the water as to get away from the foam. So the transducer is hopefully then just looking at the actual surface of the water and not the foam. So yes, the foam will interfere with the reading that you'll get back from the ultrasonic. Conrad, since you're my PA today, can you make another note for Trevor? I think I have some information on detecting foamy waters with ultrasonic. I'd like to forward that to him. Thanks, Conrad. All right, so we're going to be having a look at dual duty ratings, Annexure 11 in our 2020 catalog. So to me, this is quite an important topic. A lot of our clients, are not aware of this, about the dual duty ratings that some drives enjoy. The one I would like to highlight here, and the one that's in the annex in our catalog, is the ME and the MS 300 drives. So by default, these two model drives have a heavy duty rating. So 150% overload for 60 seconds or 200% for 3 seconds. So that is, in fact, a very heavy overload capability of these drives. This is the default rating of any ME or any MS drive. The second rating that you can activate through a parameter is normal duty. So normal duty only at 120% for 60 seconds and 150% for 3 seconds. Normal duty is typical for fan and pump applications, where heavy duty is typical for conveyor, crusher, compressor, maybe even a spindle drive, for instance. So if you have a pump application, please be aware that a 0.4 kilowatt, or let's go with the sample we chose here, 2A7 ME43, this drive. So you chose a 0.75 kilowatt ME. It's rated at 2.7 amps, heavy duty, just as the name suggests, 2A7. If you select the light duty component of this drive, the rated amps is actually 3 amp and typical kilowatt about 1.1. So this is common for every single M series drive. The default duty rating is heavy and the alternate duty rating is normal. Okay, important to remember. A couple of cases, a client would have gone, okay, 0.75 not enough for this application. I need 3 amp, so let me go for the 1.5 kilowatt. Not knowing that there's a second duty inside of that same drive that will give you the 3 amp you need for a pump or a fan or a lighter application. Got an anonymous here. What is the most compatible version of software can be used to the drives, PLC, SCADA, etc., if it can be done? Software can be used. Well, in terms of the PLC, it's ISP soft that would control the PLC. In ISP soft, you could easily have data tables set up to read multiple drives. If you're looking at from the drive's perspective, you would use VFD soft to set up parameters or just the keypad. And from the SCADA side, you would use the DIA view software. Sorry, Anonymous, I'm struggling to decipher your question. Maybe you can ask it in another manner. I'll carry on until we get maybe a clearer question, or my lack of understanding maybe. So we'll carry on with the heavy normal duty. So it's important to note that the ME and MS has an alternative duty, and that alternative duty has actually a higher rated current than the original or the default duty that is advertised. All right. Granules or maize, 100% ultrasonic. Definitely ultrasonic sensor, Hadman. We've done quite a lot with grains and maize and things like that. Definitely ultrasonic sensor. For level control, and it's a liquid, diesel or water or something like that, I suggest a 712 because you don't need to teach the device. You can just immerse it in the water, and if you know the density of the fluid, you can easily work out the level. But with grains and etc., no, you need ultrasonic sensor, definitely. Okay. So having a look at the dual duties from a graphical point of view, our blue line is the heavy duty rating. So that is our default duty rating of the drive. You can see that we can supply a lot of current initially for that heavy startup application, your compressors, your crushers, etc. And then the 150% for 60 seconds is higher than that of the normal duty, but the actual nominal running current is lower than that of the normal duty drive. So you can see by this graphic, this is a 5.5 ME example, that the actual running current is lower if it's on a heavy duty than in a light duty application. Okay. It's all about averaging the load out for the drive so the drive won't trip. You can set it to a heavy duty state with high impact, high starting torque. It can ride through that initial troublesome startup. But by doing that initial heavy loading, to ensure longevity, the rated current, the long operating current of that drive is much lower than that of a normal duty. In a pump or a fan, you've got a relatively easy startup, typically like that. And because of the startup is so gentle on the drive, it allows the designer to have a higher nominal running current. I hope this chart explains it. So like I said, compressors, crushers at that point. Okay, so the question come again, you like to combine drives with PLC, SCADA, etc. Can it be done? So obviously SCADA is then your overall, your overseeing application. So from your SCADA, you could run most likely Ethernet out to a PLC, directly to the PLC. From the PLC, I would then go from the PLC perspective then down to the drives. So SCADA to PLC, Ethernet, PLC to drives, depending on the quantity of drives, I would say RS485. RS485 is built into our PLCs, it's built into the drives, so that'll be your most cost-effective solution for the control layer. But SCADA to PLC, Ethernet. If you wanted to go SCADA directly to drives and directly to PLCs, it's also possible. If your PC has a serial port, you could COM directly to the drives of a serial, or alternatively add Ethernet cards to your variable speed drives, and then have your SCADA talk directly to each drive over IP and talk to the PLCs over IP as well. But like I said, the typical control layer structure would be SCADA, Ethernet to PLC, and then PLC either CAN open or RS485 or something else to the variable speed drives. That would be my suggestion. Yes, definitely possible. Yes, we've done it before. But starting at SCADA, PLC, and then drives in that format. So another slide on the dual duty ratings, just to highlight what range drives have dual duty or not. So like I said, MEMS, the default duty is heavy, all right? The VFDE, its default duty is heavy, but it doesn't have an option for alternative duty. So what you, the current and the overload capability you have on the drive is what you're stuck with. The CP and the CFP is default of light duty because it's the pump drive. And if you have you can set into a normal duty. The C2000 is normal and it can go to heavy. 690 volt has a slightly different arrangement. And then the ED drive is heavy duty by default with no alternative duty. So why am I highlighting this? I'm highlighting this for this reason, that the M series drives is the only range of drives that has an increase in nominal current with the alternative duty. All the other drives typically would decrease the nominal current, as the default duty is not the highest. Only the M series drive has a heavy duty as default, which means changing the duty would increase your nominal current, but obviously decrease your overload capacity. Okay, important to note, I've gotten quite a few customers and even some of our colleagues caught them out by not offering the alternative duty and rather sizing the drive one size up, which does price you out a little bit sometimes. So important to remember. I want to highlight our ME drive versus its predecessor, the EL series drive. So as most of you will know, that the EL has been discontinued from EM's perspective. It's still available from Delta, but we've decided to go with the ME300. It's better in every aspect, up to 60% size reduction versus some of the models on the EL. You can see by the footprint and the dimensions here that the ME is much more attractive in terms of its space. It also has bottom entry, bottom exit terminals, which is more suited by most users rather than the EL's top entry, bottom exit. And also a very convenient side-by-side mounting installation. The 400 volt drives are much the same versus the old EL, very, very compact. And another advantage of the ME is in our economical drive, we're going up to 7.5 kilowatt. So versus the old EL, we would stop at 3.7 and not have an economical function, say for 5.5 and 7.5 kilowatt. But with the ME300, we have that 5.5 and 7.5 kilowatt economically priced. So that's a great addition to have to us. And you can also see the dimensions compared to, say, the E drive is much, much smaller. There's also a built-in braking chopper on the ME300, where the EL would always be an external braking unit. And this would add a huge amount of cost if you needed to do braking with the EL drive. Not only cost, but also footprint and setup. So all ME drives, even though they are low-cost options, have built-in braking transistors. All right, we're nearing the end. I just wanted to highlight again our VFD options and summarize it. So the ME300, max power, 7.5 kilowatts. The key feature, compact, economical. We can't add on field bus. There's no internal PLC. There's no options for closed loop control from a motor encoder. And we can't add on additional analog or digital I/O onto the drive. So important, there's no field bus add-on. There's already Modbus built in though, but no field bus add-on. The MS300 is compact as well, but smart intelligent drive, up to 22 kilowatt. Plenty of field bus add-on options, 2 K-step built-in PLC, no closed loop control from a motor perspective, and no add-on I/O. Our CP2000 is a pump specific. This is wrong, it's actually 560 kilowatt now. Add-on field bus, very large internal PLC, no closed loop because we don't need closed loop for a pump application, and a host of add-on analog or digital I/O. The CFP is much the same, except the max is 90 kilowatt. And again, no closed loop control because you don't need that on a pump. Can the M series be used in parallel? Do you mean two drives on at the same time onto one motor, Trevor? No, no, not two drives to one motor at the same time. I'm not aware of any drive that can do that, to be honest. There are functions in the M series drive to have one drive and two motors, and you can set up two different overload tolerances or two different motor setups and have the drive run one motor through a contactor and have it run the other motor through a separate contactor independently. Or you can have one drive with multiple motors running at the same time at the same speed, but you cannot run the M series drives with active outputs and paralleling those outputs up while they're active. No, will not work. It'll trip. The C2000 is full of features, and you can see it checks every single box. Plenty of field bus, internal PLC for days, full closed loop, and plenty of I/O add-on. So that's our full feature drive, the C2000, and then obviously the elevator specific drive. Only need to support closed loop control to get that precision control on elevator stopping and starting, etc. So that's our drive series in a nutshell. I hope you guys enjoyed it. That's all from me. 2 minutes over 1 hour 15. Conrad, anything from your side?
No, just a big thank you to everybody. It was a really interactive session, and we really found the questions that were being asked really interesting. You know, happy we could answer all of them, that we weren't stumped by any questions, but yeah, I just hope it reinforces that EM's here to offer high-level technical support to all of our customers. We have in-depth knowledge of the products that we sell, and we're happy to assist if a client has an application to help them choose the right products for the application, so that your customer, the end user, has a wonderful experience with our products.